Hello everyone, in this video we will walk through the famous paper from Rivest, Edelman and Dertozos on the data banks and privacy homomorphisms. This paper is really important in terms of the history of fully homomorphic encryption because it in general is counted as the first ever serious attempt towards FHE. In this paper, they propose a problem, and they propose several alternative solutions, all of them based on the same idea. So let's see how they did it and what kind of points we can get from this paper. So the question is, what if we could perform computations on encrypted data without needing decrypting it? Even today, it sounds futuristic in terms of practicality, but back then in 1978, it was super futuristic. But as you see here, this idea was proposed like 48 years ago. And in this video, we will walk through this paper. So, of course, almost as all the papers and mathematics starts with introduction, and they will go for a concrete example and what kind of solutions they could explore and propose. So the problem obviously is the same as we dealing with right now, like what kind of setup we can use so that some sort of input could stay encrypted and also allow any sort of operations on top of them. Of course, back then it was not any sort of operations; it was limited to some kind of well-known operations. But yeah, let's see. So they start with a example they call a small loan company, which uses a commercial time-sharing service to store its records. The loan company's data bank obviously contains sensitive information, some sort of sensitive financial information, I suppose, and of course they should be kept private. On the other hand, let's suppose that the information protection techniques employed by the time-sharing service are not considered adequate by the loan company. Here we have to find a way of, storing everything encrypted, but also not needing decryption in any middle steps. So there is a good figure here expressing the main idea. There is a data bank files, there is a computer system, and there is a presumably physically secure environment, which, in which user terminal and encoding decoding processes take place. This organization permits the loan company to utilize the storage facilities of the time-sharing service, but generally makes it difficult to utilize the computational facilities without compromising the privacy of the stored data. The loan company, however, wishes to be able to answer such questions as what is the size of the average loan outstanding, how much income from loan payments is expected next month, how many loans over $5,000 have been granted. These questions require computation for their answers, and here it starts the tricky part. Yeah, they inspected 4 possibilities. The first possibility is to give up the idea of using the timeshare service and purchase an in-house computer system. Second, use the storage facilities of the time-sharing service only to store the encrypted data and use an intelligent terminal at the loan company office to do the necessary decryption and computation. Third, persuade the time-sharing company to make hardware modifications to its computer, allowing the data to exist in decrypted form for brief moments inside its CPU, but such that the decrypted data is not externally accessible. This one could sound familiar. Use a special privacy homomorphism to encrypt its data so that the time-shared computer can operate on the data without the necessity of decrypting it first. This is the coolest one. Option 1 can be very expensive, totally. Option 2 would work, but entails rather large communications costs in general. correct? Third one is also workable, but requires the cooperation of the time-sharing company. 4 requires only that a suitable privacy homomorphism to exist, and that the loan company obtain an encryption-decryption device implementing this homomorphisms. So, solution by hardware modification. In figure 2, which we have here, we will get back to it, we present a sketch of how computer system might be modified to solve the problem of performing operations on encrypted data securely. In addition to the standard register set and ALU, a physically secure register set and ALU CD are added. All communication of data between main memory and the physically secure register set passes through an encoder-decoder, which they call E, supplied with the user's key so that unencrypted data can exist only within the physically secure register set. All sensitive data in main memory, in the data bank files, in the ordinary register set, and on the communications channel will be encrypted. During operation, a load or store instruction between main memory and the secure register set will automatically cause the appropriate decryption or encryption operations to be performed. So in this figure, we see a diagram with data bank files, the main memory, there is an interaction between them, input-output flow, standard register set, they call A, and standard ALU, B, and this is the physically secure environment. So the obvious problem is getting the encoder-decoder loaded with the user's key K without compromising the security of the user's K. One possible approach is to keep the user's key encrypted under control of a system KS. The encrypted form of K, like E of K, can be transmitted over the insecure channel to the system, decrypted by the physically secure decoder and loaded into decoder or encoder. This is a key exchange problem, obviously, and we need to keep in our mind that this paper was written in 1978. So, besides the problems of key management, there are questions of the speed degradation caused by invoking the encryption or decryption with every load or store. However, it appears that suitably secure encryption, let's say DES, can be performed on a time scale comparable to that of the instruction execution of many machines. Let's go through the final paragraph. The most severe restriction on this solution, however, is one that will turn out to be a restriction on any solution to the problem, even privacy homomorphisms. It is not possible to simultaneously preserve security and give the system the operation of performing comparisons against known constants. That is, we may not give the computer system a means of performing operations sufficiently powerful to enable someone who knows only E of K to decrypt the data. The ability to perform comparisons against constants would allow someone to perform a simple binary search procedure to determine the decoded value of any single data. We examine this restriction in more detail future. So, now here is the main part, the privacy homomorphisms. Homomorphism, like the concept of homomorphism, comes from algebra, and we all have homomorphisms in almost every single algebraic structure, especially in groups and fields, or rings. They simply are some sort of mappings or functions from one algebraic structure to another, but preserving the main structure of the corresponding algebras. Here we have the unencoded data and some sort of operations to be performed on. In our case, it would be like, comparing if any sort of operation was greater than $5,000 or not, or something else regarding financial computations. Also, we have a set S, some operations like F1, F2 till Fn, let's say. We have some predicates P1 to Pn or M, and some distinguished constants S1 to Sl. We denote this system by this, with these functions, with these predicates, and these constants. So we have like this notation by like these fundamental operations, comparison, and these fundamental numbers. And writers also specify that in addition to the algebraic system of the user, let's say U, we also need another algebraic system C to be used by the computer system. You can think of it like client-server relation. Encoding and decoding shall then mean mapping elements from U to C or vice versa, respectively. It does make sense, right? There are some elements in user's algebraic system, and we want them to be stored or something else to be done in computer system, but as we discussed before, we cannot trust the computer system, so we need to encode our data before sending to the computer system. And at the end of the procedure, and at the end of the confidential operations, we want to get our data back, the resulting data, but to be able to read it, we need to decode it after, of course, receiving it from the computer system. This is the more formal expression for this. And yeah, here is the part. We have phi, another function, and let's say like the phi is the decoding function from S prime to S, and the inverse obviously should be the encoding function, psi inverse, and it's obviously defined from S to S prime. In order for the system to be able to operate on the encoded database without decrypting it, the decoding function phi must be homomorphism. This is really important. If you're familiar with the homomorphisms and other relevant algebraic structures, this one should be very intuitive for you. But if I need to explain it on simpler terms, it's basically defined between two different systems, in our case, user and computer systems. These two have different data types, different structures from the algebraic perspective, and this phi function, decoding function, or phi inverse function, encoding function, are defined from these different algebraic sets. So it has to obey the rule of homomorphism or axioms of homomorphism to not to break the structures of these algebraic structures. Okay, so let's assume simply user asks the system to compute, let's say f1 prime of phi inverse d1. Phi inverse d1 means phi was the decoding function, phi inverse was the encoding function. So phi inverse of d1 means user wants to decode the data called d1, and also the data corresponding to d2, and they want to apply this function to these two encoded data. Since phi is the homomorphism from the very basic nature, it gives us what we actually want. All right. So, okay, we have some requirements to choose the algebraic system C, and determine the functions like phi and phi inverse, decoding and encoding. First, decoding and encoding functions should be easy to compute. Of course, this is in terms of efficiency. The operations f prime I and predicates p prime I in C should be efficiently computable. Another efficiency requirement, an encoded version of a datum or a single data, di, corresponding to encoding of di, the same, should not require much more space to represent than a representation of di. This is really important from the practical point of view, because In not homomorphic setup, you basically store your data in the plain text form. Let's say it's DI, and it's like it's a like it's a space it represents in the database, right? But in the new version, in the homomorphic version, we're storing the encrypted or encoded version of our data instead. And so it's a ciphertext, not a plain text, and the size of ciphertext should be, that bigger than the size of plain text. Knowledge of encoding function for many data DI should not be sufficient to reveal phi. Ciphertext only attack. Yeah, this is one of the very well-known attacks in cryptanalysis. So that assume there is a case where when you have only one single ciphertext, you cannot reveal any data or any information out of the ciphertext regarding its plain text version. But once you have, let's say, more than a threshold number of ciphertexts encrypted under the same encryption scheme, you might have some chances of extracting some information regarding the key or encryption scheme. There are some examples of it. So our scheme has to be resistant to those kind of attacks. Knowledge of DI and encoding of DI for several values of DI should not reveal phi. This is the chosen plaintext attack. It's really similar. The operations and predicates in C should not be sufficient to yield an efficient computation of phi. Yeah, this basically relates to primarily to the use of comparisons. So there are some simple observations. If the operations available in the computer system allow the computer system to determine the encoded version of arbitrary constants and a predicate, let's say less than or equal to, for a total order is available, then there is no secure privacy homomorphism from C to U. But why? Because it follows from a simple binary search strategy. For example, for a system of natural numbers, like the set n plus addition operation, order 0 and 1, and another algebraic structure C with let's say some set W, addition, order 0 and 1. The malicious systems programmer on the computer system can decode the encoding of DI by computing the encoding of 1 and encoding of 2, and so that it could solve the underlying algorithm, and he finds a number k such that encoding of 2 to k is actually reveals the encoding of any data they want to reveal. So this is also a cryptanalytic security. This is another one, and yeah, another good and important chapter, some sample privacy homomorphisms. So the first one, we have a finite group with a prime p, and addition, subtraction, they're essentially the same. So, and we may choose the computer system structure with the set of integers modulo some number n, which is a product of two large primes with the operations of multiplication and division. Of course, there is a generator G. Then we choose the encoding function. So to perform the underlying data by putting it on top of the generator. So let's say we want to encrypt 2 or encode 2 in this context. We just put the 2 on top of the generator point modulo n, and the resulting number is the encoding of 2. And of course, the decoding function is the inverse function, base G function. You can easily check that by the laws of exponents, phi is a homomorphism. This was the main requirement, and this algorithm consistently applies. Another example is going through like equality test, and this one this this may look quite familiar. Here from RSA. Another example is simply yeah having the user algebraic system like another prime group and having these operations and like representing each prime field element or a group element by a pair of numbers. One number is the underlying number modulo p, a prime. The other part of the pair is x modulo another prime number. There is also two more examples. They are based on different hard problem, as always in the cryptography, but all of them are based on integers simply. So this was the main walkthrough, and this is like relatively short paper of like 11 pages, and the importance of this paper lies on the fact that this was like almost 50 years ago, and also it was the very first serious attempt toward using cryptography to ensure about privacy. Another thing I really like about this paper is actually, it's based on a real world problem, right? The loan company problem, and like the confidentiality of financial data. This is even today is a huge problem in both traditional finance and also decentralized finance because of the publicity of blockchains. The other thing is, by the way, like the first point is like this is not something common in most cryptography papers. Like this, something like this practical example. The another thing is, as it should be, it determines some sort of concrete requirements before directly going forward to choose like the algebraic systems, the user systems, and corresponding homomorphisms. And after stating these requirements, it makes some relatively simple observations, and all these preliminary steps makes it ready to go forward directly. And another good thing is they provide like 5 different examples satisfying what they propose. They're not only saying, okay, this is a good idea, let's use homomorphisms as encryption schemes so that we can ensure, like, let's say, some sort of privacy in confidential data. But they also provide 5 different examples in terms of schemes that can be used in the practical world. Of course, the final point is this was the very first step towards FHE, and like the Gentry's paper came along in 2009, which means there are 30 years between these two papers. But most people naturally doesn't know about the fact that this 30 year wasn't empty. Like there are many people have been worked on like different part of the problem, and they proposed different kind of solutions to some sort of restricted areas of the main problem, and all those accumulated knowledge made FHE possible. This is my personal view, obviously, but the aim of this video playlist will be to unveil like the all these efforts, as much as possible. So as this paper was the first one, this obviously has to be the first video. I hope it was interesting, instructive, fun, and easy to follow. I tried to make it as easy as possible to follow and understand the ideas instead of reading through the entire paper. So yeah, thanks for watching. I hope you would be here to watch another videos on another papers, and I hope it was helpful.